So here's some tricks for our definite integrals. So trick number one, we switch the endpoints, then we change the sign of the function. So if we're going from 10 to 4 of f of x, but we want to go from 4 to 10, then we can go ahead and switch them as long as we change the sign. Remember, when we're just doing this, we're getting f of b minus f of a. So if you want to make it into f of a minus f of b, that's fine. But now you're backwards and you're subtracting, so we just put a negative in front and everything goes back to normal. So here's an example of where we want to use it. We don't want to go from x to 2, we want to go from 2 to x, so we get a nice formula. So we can take and put a negative in front, put 2 to x, negative t cubed minus 5 dt. And then we can distribute that negative, and now it's from 2 to x of t cubed plus 5 dt. So this is an example of using it. If you want to switch the letters, just change the signs. Okay. Trick number two. We can split up our integral into different parts. So we can go from a to c, and then from c to b, and find that area, and then we just add them together. So, with our absolute values, we can't really use the absolute value, but if we look at it, our absolute value of x looks like this. And we're going from negative 1 to 2. And so we want to find this area and this area. And so you can see we now have two different functions right at 0. So we can break it up into this. Negative 1 to 0 of our absolute value of x dx plus, and then go from 0 to 2 of our absolute value of x dx. Well, if you remember our absolute value of x, we can make into our piecewise function, which would be negative x for all x values less than 0, and positive x for all x values greater than or equal to 0. Doesn't really matter we put that equal, just nice to be there. So we can say, well, these are less than, and so we make it into x dx, and these are greater, let's put a negative there. And so we do x dx, and now we can find our integral. So just think about it, what it is. It's the area under the curve, and if you need to break it up into parts to make two different functions, one for y equals negative x and one for y equals x, then you can use the integral from negative 1 to 0 for y equals negative x, and from 0 to 2 for y equals x, and then add them together to find that full area. This is our last trick. Integrals have symmetry. So if you can see symmetry in stuff, well, then you can just use that symmetry to cut down our interval. So let's just say we have an even function like f of x equals x squared. And we want to go from negative a to positive a. So the same distance from 0. Well, if you notice, this area here is exactly the same as this area over here because it's an even function, and even functions have symmetry across the y-axis. So what we can do is go, okay, well, why don't I just find this one and double it? So we can go to integral 0 to a of x squared dx. And why would you want to do that? Well, 0 is amazing. Remember, when you plug it into these polynomials like this, you get 0. So all we'd have to do is deal with a. Well, what if you have an odd function? Odd functions are great as well. So if we're going to go from negative a to positive a, you can see that this one is actually negative and this one is positive, but they're symmetric across the origin. So this area here is exactly the same as this area here. So if you can mark it off negative a to a, you know it's 0, because you're going to get a positive version and a negative version, and they're just going to cancel each other. So those are your tricks.